Hello anyone, and welcome to another Roadmap of the Stars, professional as always and without flaws. We don't have too many events going on this fall, but the events that we do have are pretty spectacular and pretty fun to spot. Before I get started with the show though, we're gonna kind of switch things up on how we do this today. I know the last couple times I've done this show, I usually try to aim for not going over an hour, but the last time we did this show, it was almost 3 hours long. So, I'm going to kind of switch up how we do things today. I'm going to start with the astronomical events of fall, and then I'm going to use the remaining time that we have left to go over some constellations that you would be able to see while looking for these events throughout the fall months. I also want to do this because I've been doing this kind of show for a long time, and I've gotten a sort of rhythm, especially with the constellations part of the show, in such a way that it's not scripted, but I tend to follow the same pattern each time, and I try to get through patterns before answering questions, and sometimes I end up losing people because they think I'm not watching the chat. So hopefully this way, by really shaking things up, I'll be forced to kind of go more off the cuff, off of any sort of pattern, and hopefully that will make me a lot more interactive. Becca was looking at me. I don't know if something is up with the stream.
No, I just think...
Oh, okay. So, what we're going to start with is one of the events that we always talk about during this show, because since this is a quarterly show, I always plan them to occur normally on the Saturday before a season change. We had some events that came up the other day that we were like, oh, we got to reschedule quickly. It's okay because we're bad at advertising and we're bad at business. So we moved it to Sunday. But with that being said, the first event that we end up talking about is the season change, and this particular season change is going from hot, boiling summers to more I lost the word that I wanted to I lost the word that I wanted to use, but tolerable. Yeah, a more tolerable.
Changes.
I don't know why, but your voice is coming in very strange, very robotically. So try to just talk loud enough to get into the microphone.
Okay.
So anyway, sorry. There's a lot of things I didn't test for before this stream. So we're going into fall. Now, why do we have seasons at all? The Earth is constantly orbiting around our sun. And depending on how the Earth is facing the sun will dictate what season that a certain hemisphere experiences. So, as you can see, our Earth that's orbiting the sun, these red points here, these red sticks sticking out, this is the Earth's axis. This is what it rotates or spins around. Kind of like a top. When you spin it on a table, it as it spins, it's staying balanced. The whole top is spinning around the handle because the handle is the top's axis of rotation. Well, these poles are the axial poles. This is where the Earth's handle would be if it had a handle, right? It's spinning around these imaginary axes. and they are tilted by about 23.5 degrees. Now, that makes it so that during the winter months, we in the northern hemisphere get less sunlight because our hemisphere is tilted away from the sun's light coming at us. More of the southern hemisphere gets it. So to Australia, December is summer. To us in North America, December is winter because we are in the northern hemisphere, Australia is in the southern. During the summer equinox, the summer solstice, the northern hemisphere is more pointed towards the sun, so we are getting more of the sun's rays coming at us, and the southern hemisphere is getting less of the sun's rays. So to us in the northern hemisphere, June is summertime. To the Australians, it would be winter. And then we come to what we're approaching, the autumnal equinox. So the autumnal equinox gets its name because autumnal, autumn, fall, and equinox, and that's the important bit, because the word equinox comes from the Latin words roughly equa, which is roughly equal, and nox, which means night. Equa nox, equal night, because during the equinox, that is the closest point in the Earth's orbit that will experience as close as we can experience to an equal day and an equal night. Roughly 12 hours of day, 12 hours of night. Equinox, equal night. So when the solstice, or not the solstice, the equinox, the autumnal equinox coming up, is not on the 21st, it is on the 22nd. The Earth, in its orbit, will put the sun right above the Earth's equator at about 8:31 in the evening on September 22nd. So why is that? Why is it that it's actually on the 22nd this year, when, if you look at a calendar, a lot of times it will default it to the 21st.
Yeah, I learned that it was
the... Becca says she learned that it was the 21st in school. And the reason for that is because it was easier. A long time ago, we had calendars long ago whenever they decided that they would just default the solstices and the equinox to the 21st. They had calendars, and they had an understanding that the equinox and the solstice didn't exactly lie on the 21st. But the Christian church, they had holidays that they set based on astronomical objects. And as on the dot as we want the Earth's orbit and the Moon's orbit around the Earth to be, it's not. An actual year is, I think, 365 and a quarter
days.
Whereas the Moon's orbit is not 30 days, it is about 29 days, right? So these aren't exact enough, and Easter is a good example of this. Easter was a Christian holiday that occurs on the first Sunday after the first full moon, after the vernal equinox, which is the spring equinox. So you can see why that would get a little convoluted, right? It has to be the first Sunday, which I guess, like, you know, what date it is on a Sunday isn't the same as it was last year. After the first full moon, which also isn't exactly 30 days, so that changes throughout as the years go by. Where the full moon actually lands drifts a little bit. After the vernal equinox, which is not always the 21st. It can be somewhere between like the 19th, maybe the 18th, up to the 21st, maybe the 22nd. Whereas the autumnal equinox can range from pretty much like 20 up to September 20th up to September 23rd. So it was very, very hard for everyone to know where everything lands, because while astronomers love looking at the sky and love knowing where everything's at, not everyone actively does that. So people would always be like, when's Easter? Right? So the church was like, all right, we need to standardize this a little bit. And so they were like, from now on, the church is going to recognize all the solstices, or both of the solstices and both of the equinoxes, to be on the 21st of their respective months. And this is what's called the ecclesiastical equinox. So, what is today? 19th? 20th?
19th.
It is the 19th. So the ecclesiastical equinox is going to be on Tuesday? Yep. But the astronomical equinox, the actual equinox, is on the 22nd. And that has to do with some complicated movements about how the Earth's orbit precesses and the fact that a year is not exactly 365 days.
So, if you hear someone on Tuesday say, it's the first day of fall, if you want to burst their bubble and be that guy, you could say, well, actually, the first day of fall is tomorrow. It will be Wednesday, the 22nd.
So now we know why seasons happen. Actually, that's a pretty solid thing, but I want to show you some other graphics just because they're kind of fun, because like watching the Earth go around, it's great and all, but why do we have shorter days in the winter and longer days in the summer in the northern hemisphere? And that again has to do with the tilt of the Earth's axis. So we have here, as the Earth is going around the sun, the axis is pointing, or the northern axis is pointing away from the sun. So when we come around to daytime, the sun appears lower, closer to our horizon. And this is an example of solar noon, where the sun is right on the Earth's meridian every single day. Oh no, you can have pumpkin spice anytime. I actually made a joke one time that it was kind of a Cinderella-esque joke, where legend holds that the second that the Earth, or the second that the sun is right above the Earth's equator, all the lattes in the world turn to pumpkin spice.
The other day, Cindy, about a couple weeks ago, I was starting to feel a little blue because I was like, summer's starting to wind down and I don't know if I'm ready for this seasonal change. And James made me coffee with cinnamon, vanilla coffee with cinnamon. And it was just to show me that there's, stuff to look forward to, even though the days get shorter. And it was delicious. So I've kind of already initiated the coffees of the season.
I'm really excited about doing homemade apple cider too. That's going to be amazing. But anyway, so what we're looking at here, this might seem a little weird. This is what's called solar noon. This is the sun when it reaches its highest point in the sky on a given day, or rather when it crosses the Earth's meridian. which is the line that connects directly north and directly south. So during the summer, we see that the sun appears to make it higher in our sky on any given day because our sky is more pointed towards the sun. Whereas, as we go in the winter, the sun appears to get lower in our sky in terms of how high it can get in a given day, until it appears to stop getting lower, and it's because the sun is now lower in our northern hemispherical sky. So this is also, I explained the origins of equinox, equal day, equal night. Solstice, like the summer solstice and the winter solstice, get their name from solstice, or sun still. Sol being sun, stis meaning unmoving, unchanging, not going anywhere. And that's because at the summer solstice is where the sun reaches the point where the sun is as high over our North Pole as it can get, and then as we go around the sun again, we're seeing it get lower and lower into the sky, where it'll stop, or solstice, down here, and then it'll go back up again. And so that's also a good reason. One, this is the reason why days are shorter in the winter and longer in the summers, because the sun is up longer. But this is also why it gets warmer in the summer and colder in the winter. Because one thing, when I was in elementary school, it's completely understandable that a lot of people hear that the Earth is closest to the sun at some points and further than from the sun at some points. And so, then you think, oh, I know when I'm close to a candle, I feel warmer, and when I'm farther away from the candle, I don't feel its warmth much anymore. So it's really easy to connect these two together. But in actuality, that's not the case. The reason that summers are warmer is because more of the sun's energy is hitting our northern hemisphere, and that energy is getting turned to heat, and that warms up the northern hemisphere. Whereas in the wintertime for the northern hemisphere, less of the sun's light is hitting us in the northern hemisphere, so that's less energy from the sun turning into heat, so it's cooler in the northern hemisphere. For us in the northern hemisphere, in actuality, funnily enough, the winter solstice is one of the closest points the Earth is to the sun. So that's another thing to kind of help you draw back from the idea that your proximity to the sun is what's going to heat you up. Now, don't get me wrong. Mercury being so close to the sun is very hot, but that's because it being closer to the sun, a lot more of the sun's energy is hitting it at a given time. Whereas we are further away from the sun, so its energy is more spread out before it actually reaches us. But this closer and further away from the sun for the Earth in its orbit is not enough to change a season. It is purely just by the tilt of the Earth.
Question.
Yeah.
Okay, so it would be, say summer would be warmer because, in my mind, it's two reasons.
For the Northern Hemisphere.
For the Northern Hemisphere.
Right.
Because, one, we have more daylight, so there's more time for the sun's rays to hit and warm us. But I also heard it's like, because rays are more direct, like, as opposed to...
Yes, both of those are true.
Okay.
And that's what I was getting at when I'm saying more of the sun's energy is hitting the northern hemisphere. Like, these lines, if we were to represent the sun's energy that reaches Earth by these arrows, we see more of the arrows are hitting the northern hemisphere than are hitting the southern. Whereas in the winter, we have the opposite. And yeah, I mean, if the sun was up all the time, like if the Earth stopped spinning and just always faced the sun, it would get very hot.
Right.
Right. So, So it is in part because of longer days, but also because more. But what I was getting at was the more of the energy in general is hitting the northern hemisphere.
Following the arrow metaphor, I think what I was thinking specifically is like the arrows can be a little shorter in the summer, and in the winter when whatever, you know.
Really it's not that they're shorter, it's that less of the arrows hit our hemisphere.
Okay.
Right? Because we see here 4 of the arrows that we're representing are hitting the southern hemisphere in the winter. Only 1 of the arrows are really making it to the northern hemisphere, right? That's the idea of the arrows.
Okay.
So, but both of those are
like,
true.
The angle, like, you know, have to go further, light would be cut out.
It's kind of true too.
Okay.
Yeah.
Can you go back to thing with the cat? Go back to with the cat.
Mm-hmm.
Can I the arrow to ask a question? An arrow that can be seen.
Yeah. Here, click and drag. Like you click and drag it.
Okay.
Yep.
So I understand. It's like, you know, astronomically, the sun is always making the same. You know, well, it's not moving, but it would be.
It is making an arc across the sky.
Right. And we're just seeing more of that arc when it's higher. So
Right.
it's like this, so it's up longer.
Right.
But then it's like, as it goes down,
that
it's
arc is
like,
going down too.
Yeah, like we're just seeing only the very top of the circle. And like when we get to the very bottom, it's like the very top of the circle. So there's just less time. It's like we see less of the circle.
We see the sun for less time, right?
Yeah,
because...
so that's the days are shorter.
Yeah.
Okay, got it.
All right. Does that make sense? Does that all make sense about seasons, why seasons change, and why it gets colder and warmer?
And why my coffee is always cinnamon.
Yeah, I mean, I guess that I can't prove I can't prove a causal connection between the two, but they are certainly correlated. Yeah.
Got it.
So
the next topic.
Yeah, so the next topic we have is on October 21st. We have what's called the Orinids. And the Orinids are a meteor shower. Now, first, why are they called the Orinids? They're called the Orinids because they appear, or the meteors appear to radiate outward from the constellation of Orion. Now, we just passed probably one of the most spectacular meteor showers of the year. That being the Perseids that usually occurs around June-ish.
No, it was later.
Was it?
Yeah.
June-ish, July. Or August.
August. Proud of you.
August comes before June. I know this. So, the reason that the Perseids, everyone loves the Perseids so much, is because the meteors that occur from the Perseids are so much brighter, and there are a lot more of them. When we talk about meteor showers, we talk about them in a way of ZHR. And what that means is meteors per hour. So if you go to look at the Perseids on its peak night, you have a good chance of seeing 100 meteors in 1 hour, or a little more than 1 meteor per minute. So it's very easy to see shooting stars or meteors. They're the same thing, just colloquially they're called shooting stars. You have a higher chance of seeing them during the Perseids because they happen pretty much almost every minute on peak night. The Orinids, however, are not as impressive. They are great, but they're not as impressive. So this is a very crude idea of the Perseids. If you take the time, you can count that there are 100 streaks here, and so this represents how many meteors would appear to radiate from Perseid or near Perseid in a given hour. And then the Orinids are so the Perseids are 100 meteors per hour, Orinids is about 20 meteors per hour. So quite a bit less than 1 meteor per minute. But it's not that bad. We still consider it a class 1 meteor shower. The meteors are still kind of cool, and the meteors that we see from them come from Halley's Comet. Now, what does Halley's Comet have to do with a meteor shower? Well, it has everything to do with a meteor shower. So meteor showers are when a meteor in general is a small space rock, maybe pebble-ish sized, maybe a little bigger, falling through the Earth's atmosphere. And as it falls through the Earth's atmosphere, it begins to warm, heat up, and then, more often than not, it just kind of bursts or burns out, fizzles away, before it reaches the ground on Earth. Now, the reason that happens is because, unlike out in space, our atmosphere has a lot of gas. That's what we breathe. That's how we are able to live on the Earth, because we're breathing in the oxygen and the nitrogen in the atmosphere. So this meteor is flying through space pretty much unhindered, and then when it hits our atmosphere, it's like it kind of hits a wall. And, well, it doesn't hit a wall, but imagine like throwing a marble into a big cube of gelatin, right? It's gonna slow it down. Even if you throw like a rock into water, it's gonna slow it down. So as the meteor hits the atmosphere, it starts bumping up against all of these air particles, air molecules, and they start rubbing up against them. If you take your hands, if you have 2 hands, if you don't have 2 hands, use a hand and a leg. If you don't have that, find someone to rub your back. But take your hands and rub them together as fast as you can, nice and hard, and you can feel that your hands are heating up, right? That same premise is why meteors burn when they go through the atmosphere, because these rocks are plowing through our atmosphere incredibly quickly, and they're rubbing up against the gas. That creates friction. Friction creates heat or energy, and when you get enough of it, then it will either burst, like throwing a rock in a campfire. Eventually the rock will probably burst if your campfire is hot enough, or it will just burn away. It depends on the material. So, where are these rocks coming from? Like, we know we have an asteroid belt, but why is it at certain times throughout the year do we get more than usual? And that has to do with comets. Comets, like Halley's Comet, where the meteors in the Orinids derive from, comets are balls of ice and rock, like often called, like described as dirty snowballs, and they are whipping around in space. Most of the comets that are in our solar system are way far out, past the orbits of Neptune and Pluto, way out, very far away from the sun, where it's exceptionally cold. And most of them live in a shell about a light year out away from our sun, about 6 trillion miles away from our sun, a shell around the solar system called the Oort cloud. And that shell is just comprised of hundreds of thousands to possibly even millions of icy comets. which is the leftover material that got pushed out when our sun formed, but are still kind of orbiting our sun. Now, even though most of them live out in the Oort cloud, some do have orbits that bring them in closer, like Halley's Comet or Swift-Tuttle. Swift-Tuttle is the reason that we have the Perseids. And like anything made of ice, it doesn't really like to be warm, right? If you take an ice cube out of your freezer and you put it on the counter, that ice is going to melt into water. Well, the comet isn't so much melting that it is sublimating. And that might not be a word that everyone's heard of. That's fine. Up until college, I've never had to know or use the word sublimate. But sublimation is just a phase change. So, like I said just a second ago, ice into water is a phase change of something going from solid ice to liquid water. If the puddle of water that you have kind of just sits around a little while and it's warm enough, that puddle of water will evaporate into steam. Evaporation is a phase change of something going from liquid, water, to gas, steam. Sublimation is just the phase change of something going from a solid directly into a gas, completely skipping any sort of liquid phase. And that's what these comets do. They sublimate. They turn from solid ice to gaseous steam. And when that does, it leaves a trail of rock and dust behind it. So we have a trail of, I think this is the trail of material, and we have a trail of ionized particles that are pointing away from our sun. That second tail isn't as important. What's important is the trail of debris. Because if a comet flies through the orbit of the Earth, or near the orbit of the Earth, that debris will kind of be left in the orbit of the Earth. Kind of still flowing in the direction that the comet was flowing, but it leaves a field of rocks and dust in the path of the Earth. And when the Earth orbits into that debris field, the gravity pulls in that rock and dust, and then that's what ends up burning up in our atmosphere as a meteor shower. So comets are the main reason that we have meteor showers. Now, we can have meteors without a comet because it's just pebble-sized rocks, and we have rocks flying all over the solar system, but these concentrations of meteors that make these meteor showers come from these comets flying through our inner solar system through the orbit of the Earth. Now, I wanted to talk about that because I like talking about that. I like talking about comets and meteor showers, but unfortunately, it might not be that impressive this year. If you already weren't sold on the Orionids because it's a lot less prolific than the Perseids, it yields less meteors. It's kind of a double whammy because during the peak day of the Orionid meteor shower, it's gonna be a full moon. So even if you were lucky enough, and I mean, you don't have to be too lucky because it is 20 meters per hour, but it's going to be a lot harder to spot them when the full moon is blaring up in the sky, right? So it's, ironically, a full moon, the moon in general, is really bad for astronomy because full moons, they reflect a lot of the sun's light back toward Earth. If you've been out on a night where the moon isn't up, it was a new moon, and then you went out and saw a night with a full moon, it would be really, really notable how different the sky looks with a full moon up, especially if you live in a city with a lot of smog or just water vapor in general, car fumes, greenhouse gases. That's gonna make it even worse. So I do encourage you to, if you like meteor showers, I still encourage you to try. It's not impossible to see a meteor during a full moon. It just might be a little harder.
Yeah, it's just like if it was a new moon and the moon was in the sky at night, you could see like more subtle, smaller meteors. But with a full moon, you're only gonna see them. They're pretty impressive. But I always think it's just relaxing to fly out and stargaze at night regardless. And I think the reason especially that we wanted to talk about this, even though it's a full moon, is just that it's cool that the debris comes from Halley's Comet, because Halley's Comet is pretty famous. It's a once-in-a-lifetime thing. Next time that it will come around is 2061, comet itself. But in the meantime, you can see the debris from the comet every year during Orion.
Yeah, like a little echo of Halley's Comet that you can see at least every year. So that's really all I wanted to talk about for the Orionids, because again, it's not really going to be great for viewing, but...
Just one thing that I wasn't sure if you said, I might have heard it, but the size of the comets versus... You said that the meteors are like little pebbles or little rocks, but comets, you said, are like the size of towns, right? Like, they're still rock, or,
They're mostly ice. Mostly ice with a good amount of rock. But yeah, so comets, the size of the comet doesn't always necessarily affect how prolific a meteor shower is going to be. I don't know the size of Halley's Comet. I do know that Swift-Tuttle, for the Perseids is, I think, 13 miles across. Comets are huge. They're about the size of small towns. And so when you have ice, and I say that, the meteor goes around the sun, and Halley's Comet has been going around the sun, documented history of Halley's Comet going around the sun for millennia. But why is it still a thing if it's mostly ice and it's chipped away at every time? It's because they're huge. They are very large. Now, we have actually seen comets that have broken up on their trip around the sun that just don't exist anymore. I don't want you to necessarily quote me on this. I want you to maybe do some independent research on this, or Becca can Google it if she feels empowered to. But I think it was a comet that had the nickname, I think it was Hermes? It was after the Roman god of like tricks and the messenger of the gods. And the idea that Hermes flew too close to the sun, that's why they gave this comet the nickname, because it kind of went to the sun for its roundabout trip and then broke up because it just lost all that material. It's been a very long time since I saw that, and my memory fails me often. So take that with a grain of salt. Look that up, though. But you can lose a comet, but most of these comets, especially Halley's and Swift-Tuttle, they're going to probably be around for quite a bit longer. Swift-Tuttle, maybe not as long. You have to come see our Halloween show for that. But they're huge. It would be a bad day on Earth if they ever decided to intersect with Earth. But with that said, let's move on to a thing that everyone always spots whenever it peeks up over our horizon. And it often gets the misnomer of the morning star, mainly because of when it first appears in our sky. It either appears to pop out in the morning, which is why they call it the morning star, or the evening. Sometimes they call it the evening star. Depends on who you talk to. But this object is not a star at all. This object is the planet Venus. Now, the reason that we can see Venus right now, and we can see it so well, is because Venus is the closest planet to the Earth. And it's about the same size of the Earth, and it has a very dense atmosphere that has a high albedo, or has high reflectivity. So when the sun's light hits Venus, it reflects a lot of that light toward us. Now, the reason that we can see Venus right now and not other times is because Venus is going into what's called greatest elongation. Now, greatest elongation is as the Venus is closer to the sun than the Earth is. So as the Earth and Venus orbit around our sun, Venus orbits just a little bit faster. You see it catching up to the Earth, and it gets to a point where the Earth, Venus, and the sun make a right angle triangle. When this occurs, this is what's called greatest elongation, and it's one of the best times to see Venus or to see Mercury, because a lot of the time it's not very easy to see them, because since they are in between us and the sun, there are a lot of times where it will be in between the sun and the Earth, so the sun's light blocks that out. There are other times where the planet is going to be behind the sun. Venus or Mercury will be behind the sun, and for obviously reasons, we can't look through the sun. I don't even recommend looking at the sun without special equipment, but the sun blocks it out physically, whereas when it's in between the Earth and the sun, it blocks it out more visually. It's the light that makes it so we can't see it as well. But at greatest
I just wanted to elaborate on that, because even if the planets that are outside of the Earth,
right, I'm gonna get to that.
Okay.
So greatest elongation is the best time to see it, because in our sky, it is the space in between the sun and Venus appears to be at its greatest distance apart. It's elongated. The distance is elongated to its greatest extent. Greatest elongation. And so we see up in the corner here, this is the date of greatest elongation, and this is where this is one of the points where it is the best time to see it. But it is not the best time, because it gets a little more complicated. Now, the reason that we do, I want to go off what Becca was just about to say. I want to kind of clear up why it gets so complicated, the times that we have to see, that we get to see Venus and Mercury, but I never talk about how complicated it is to see Mars, Jupiter, or Saturn. That's because I'm gonna actually bring up open space for this. That's because our solar system has what are called superior planets and inferior planets. So, superior planets are planets that are further from the sun than the Earth is. So this blue circle here, or this blue semicircle, is the Earth's orbit. Then we have Mars, Jupiter, Saturn, Uranus, and Neptune. We can't easily see them with the naked eye. Can't see Neptune at all with our naked eye. And the inferior planets, which are planets closer to the sun than the Earth, Venus and Mercury. So with all of our superior planets, the best time for viewing those is during a point called opposition, and that's when the superior planet, like Jupiter, is on the opposite side of the Earth from the sun. So it would be at its highest point around midnight, and it would be up all night long, but its highest point would be up at midnight, and it's completely illuminated, similarly to why a full moon is probably one of the better times to see, get the best view of the moon, because it's all lit up and it's in our sky all night long. But inferior planets, they never have that opportunity. They're never at a point where they're going to be exactly opposite of the Earth from the sun. They're going to be opposite of the sun from the Earth, and we can't see it. Going to be on the same side of the sun as the Earth. We also can't see it. And both the planets never have a point where they're up all night long. They usually follow after the sun, so you have a short time frame to view them even at their best points. So we can talk about, Mars and Jupiter during nights when they're up, but often I will take the opportunity to talk about Venus and Mercury because you can't see them for very long, and it's very easy to miss them if you're not out there when they're visible. Now, I said that greatest elongation was one of the best times to see them. Around greatest elongation is the best time to see either Venus or Mercury, but they are not the best time because more often than not, sometimes they align, but more often than not, there is the greatest elongation, and then there is the planet's highest point in our sky that it can reach. And its highest point above our horizon is actually on the... where do I have that? I have that here around December 5th. November 25th through December 15th is going to be the highest point that Venus reaches in our sky at about 20 degrees above the horizon. If you need a little reference for that later on, if you go out tonight and look at the constellations that I'll be talking about after I finish the events, take your fist and make a fist, hold it as far away from your face as you can, and the length between your pinky and the top of your fist, that's about 10 degrees. So you stack from the horizon, you stack two of your fists, that's 20 degrees above the horizon. That's the highest that Venus will get above the horizon throughout the fall and early winter months. Of course, as we continue on, so this is, like I said, this is about November 25th. This is November 25th. As we then continue through the months, it will be on its course back downward as it orbits our sun until it is almost in between us and the sun, where we would not be able to see it anymore because when the sun sets, it's set with it. But when I talk about Mercury for that, Mercury doesn't... When Mercury reaches its highest point in the sky, it doesn't stay there long. Maybe a month at most. But it does not stay above the horizon long. Mercury has an orbital period of... meaning it goes around the sun once every 80 Earth days. So in one Earth year, it has been 4, or a little bit more...
That's around 4.
Around 4 mercurial years. So by the time the Earth has gone around the sun once, Mercury has gone around 4 times. So it books it. It is not at greatest elongation or at its highest point in the sky for very long. But Venus is going to start becoming visible, started becoming visible around September 6th about. And we're in September 19th now. So it's been rising. It's still about 15 degrees above the horizon right now. But if you've noticed a bright object in the eastern sky toward where the sun set, that is very likely Venus. And it's very easy to spot, unlike Mercury, because Venus is, not counting the moon, the brightest object in our nighttime sky. You have plenty of time to go out and find Venus. You have all the way up until about December 25th, where it's going to be roughly 15 degrees above the horizon again. But then January 4th is when we're not going to be able to really see it anymore at all. So you have plenty of time, but go out and see it. It's a great telescope target, actually, because both Venus and Mercury, probably the superior planets as well, but not as much, but definitely the inferior planets, both Venus and Mercury go through phases like our moon does. Our moon goes through phases because it is orbiting the Earth, and as it does, the part of the moon that's lit up either faces toward us or faces away from us. Now, the moon, only one face of the moon faces us at any one point. But there is no single dark side of the moon, because the moon does spin. There would be a dark side of the moon if the moon didn't spin at all. But there's... both faces of the moon get about, 15-ish days of night, 15-ish days of light, roughly. But its phases come about because of our perspective of the moon in its orbit. So when the moon is up here in its orbit, or over here in its orbit, we see a first quarter moon. When it is opposite of the Earth from the sun, we see a full moon because it is completely lit up. When it's here in the moon's orbit, we see a third quarter moon. And then, of course, in between there, we have the crescents and the gibbouses. We're just seeing a different perspective of the sunlit part of the moon at any given night. So that's why the moon has phases. Venus has phases because as it orbits the sun, we see that when it's around here, we see half of Venus lit up, or more like a gibbous of Venus lit up. When it's over here, we see the other side of Venus lit up. When it's back here, we see even more of Venus lit up. We never see a full Venus. We never see a full Venus because a full Venus would put it on the opposite side of the sun from us. Then as Venus goes around in its orbit, we see less and less of Venus. We see it go into a crescent phase until it has gone in between us and the sun. So Venus goes through phases, and it's close enough to us that if you had a telescope, a modest refractor could probably work. I've been meaning to go out and make sure it does. Haven't yet. But you'll be able to notice phases on Venus. And that's pretty spectacular because we don't think about planets having phases, because we don't often think about planets in the same way as the moon, but they do. They would go through phases if we could see as much of the planet as we see of the moon. And with Venus, you can see that little extra. You can get a good enough view of Venus in a telescope, in a like civilian telescope, to get a good idea of, to get a good enough view of Venus's phases. So we move on to, I guess we have two events. We move on to November 2nd, which is arguably the most important day for astronomy.
Yeah, and the world, really.
It's my birthday on November 2nd. But on November 19th, we have something just as spectacular. On November 19th, earlier this year, we did a show all about eclipses, solar eclipses and lunar eclipses, because we had both a solar eclipse and a lunar eclipse that you could see from some places in the United States. The East Coast could see a bit of the solar eclipse. The West Coast could see a lot more of the lunar eclipse. But coming up, this lunar eclipse, everyone in the US is going to be able to see it. And now, an eclipse gets its name, whether it's a solar eclipse or a lunar eclipse, based on what is being eclipsed. So for a solar eclipse, the moon is in between the sun and the earth. And for a lunar eclipse, the earth is in between the sun and the moon. Now, this lunar eclipse, this isn't a lunar eclipse, I'm just bringing this up to explain this next point. This lunar eclipse is only going to be a partial lunar eclipse, but it's going to be just about as close to total as you can get without being a total eclipse. But before I get into that, what makes something a partial eclipse and what makes it a total eclipse? It's the shadow that is being cast. So here we have an example of a solar eclipse and the shadow that the moon casts on the earth. So here we have a lighter part of the moon's shadow on the earth. This is called a penumbral shadow. And the darker part of the shadow is called an umbral shadow. Now the reason that is because we have a light. The sun is not a single point of light. It is very large, and it is emitting a light from all different directions, from all points on the sun. So we have light that's coming in rays directly at the earth. But when we have this shadow being cast, we also get some of the light coming into the shadow. So these lighter parts is where we have a little more light coming into the shadow because it's not being fully blocked. And then the darker part, the umbral shadow, this is where light isn't getting to because the moon is just getting in the way. Now there is a point where if the moon were further from the earth, that we wouldn't be able to get a total eclipse anymore. We'd get only annular eclipses, which is where not when the sun is being almost completely blocked out, but when the moon gets in front of the sun and you see like a ring of light around the moon. Now, as the moon is moving further and further away from the Earth, it could reach a point where we will never have a total eclipse again. And that's because as the light is coming from the sun, it is bleeding into the umbral shadow, and it will just funnel down to a point to which then it just would be completely an umbral shadow, penumbral shadow. So the partial comes in where the moon going into the Earth's orbit is either completely in the shadow, the Earth's umbral shadow, or only partially in the Earth's umbral shadow. So I'm going to go back to Stellarium, and I'm going to kind of show you what it's going to look like to have a partial eclipse. Now, like I said, it's going to be as close to a total eclipse as you can get. But it's not going to be absolutely total. It's going to be great. It's going to be absolutely great. I know I keep saying, like, oh, it's not going to be exactly total, but the thing is, it's going to be so close that it's just going to be amazing. It's going to be as amazing as you can get to a total eclipse without having a total eclipse.
It look red?
It will start to turn a little more red. It might not turn as red as it would look in a total lunar eclipse, but it will start to turn red because, as we'll see, so much of the moon will be covered. So, we're going to get a zoom on the moon. We're going to lock ourselves to the moon. So this is the partial lunar eclipse is going to occur on the morning of November 19th. So, yeah, let's go back one and set this to midnight. It's the beginning of the eclipse where the Earth starts to go, or the moon starts to go into the Earth's umbral shadow, starts at 1:03. So as we move further into the evening, whoops. We'll start to, if you're extra astute, you'll start to notice the moon darkening just a little bit. This is the moon going into the Earth's penumbral shadow. And as it keeps going, you're going to eventually, around, it looks like, I think maybe, yeah, about 2:20, you're going to start noticing a terminator starting to sweep over the moon. Now, a terminator is the name we give if you see like a... Where's my... There it is. When you see like a first quarter moon, a third quarter moon, pretty much anything beside a full moon, that line where you have the lit up moon to the darkened part of the moon, this line that separates the two is called the terminator. I just wanted to do a little vocabulary there since I used the word. So the terminator is the line at which the moon darkens from the sun's light, and that can be applied in this sense as well. It's a terminator being cast on it by the Earth. I've lost my place. There it is. So, as we continue through the night, we're going to see the terminator sweep over the moon. And this is going to be like an early morning event, right? Like, you're going to want to get if you want to see all the way from the beginning of the penumbral part of the eclipse all the way through to the greatest part of the eclipse, you're gonna want to pack snacks and drinks and blankets, because this is gonna take hours to completely finish. But at least for the part for when the moon starts to go into the Earth's umbral shadow to when it's outside of it again is going to be a bit more than an hour and a half, kind of like an hour and 3/4. So the Earth, or the moon, will start to go into the Earth's umbral shadow around 2:20, and it'll keep sweeping across and get darker and darker until enough light has been funneled out that it will start to turn red. And when I say that this partial eclipse is as close to a total eclipse as you can get without getting a total eclipse, I really mean it, because at 4:04 it keeps going all the way until 4:04, where that is the greatest part of the eclipse. That's as darkened as the moon is going to get, but that is almost all of the moon. So this is still a pretty good event to see. Pretty fun event to see. And you will start to see the moon redden a bit, but after 4:04, you'll see the terminator sweep back. So the moon around 2:20 is going to go into the Earth's umbral shadow. And it will keep going. It'll get darker and darker. The terminator of the moon's umbral shadow will sweep across the moon until about 4:04, where it will stop and appear to start retreating again. And this is the moon going out of the Earth's umbral shadow. And then it'll be completely going through the penumbral shadow, or it'll eventually leave the penumbral shadow, but at that point it's going to dip under the horizon. That is a very pixelated tree. Yeah, I'm a little... But the main point is that November 19th, highly recommend going out to see Lunar Eclipse. We're going to do our best to remind everyone about all the events as they're coming up on the Facebook page. But this partial, air quote, partial lunar eclipse is probably going to be one of the most exciting things that you'll be able to see this fall. And those are pretty much just the notable things. I might make a Facebook post because during the fall months there is going to be another Mercury greatest elongation, but they happen so frequently. I have talked about them a lot, and so it's kind of at a point that if you want to learn about greatest elongation of Mercury, we have posts in past streams of that, but we will make a post about when it's coming up. But with that said, those are the major events in the fall months. Okay. So yeah, I'll go through some constellations. So some constellations that you would be able to see tonight if you were to go out. I recommend starting with these three bright stars that will be pretty much right above your head in the early evening, comprised of... Where are my labels? Nope. Comprised of Aquila the Eagle, Cygnus the Swan, and Lyra the Harp. We talked about this asterism of the summer triangle more during the summertime, but it is still visible in our sky throughout the fall and maybe super early. No, I'd say just about to like mid-fall, late fall. We'll still be able to see the summer triangle, and that's because it's not called the summer triangle just because it's up during the summertime. We call it the summer triangle because during the early summer months, so June and July, the summer triangle and the stars that make it up rise out of the east just as the sun sets in the west. And they dominate the nighttime sky until they finally set in the west as the sun rises in the east. People a long time ago that didn't have, like, I'm talking really long time ago, that didn't really have calendars and judged when their environment was going to get cold based on the stars in the sky. Natives in North America, they might have seen the summer triangle. They might have had a different name for it. They might have seen the summer triangle high up in the sky, and they know, oh man, fall's coming. We need to start getting ready for winter, right? When it's directly above their heads after the sun sets. But again, we did talk about it during the summertime. I'm just using it because it is very bright, but it points down to one of my favorite constellations to talk about during the fall because it's more visible than it is during the summer. Capricornus, the Myrrh goat. Now, if Capricornus sounds familiar, it probably shouldn't be too surprising, because it is one of 12 of what are called our zodiacal constellations. Other zodiacal constellations that you would be able to see at 8:30 this evening are to the right of Capricornus. You have Sagittarius and Scorpius. To the left of Capricornus, you have Aquarius, the water bearer, and Pisces. I think Pisces is still a little under. So Aquarius for now. But as the evening goes on, you'll have Pisces rise over the horizon, wrapping around a constellation that I really wanted to get through because it's a set of my favorite fall constellation. So Capricornus is it's easy-ish to see, but not terribly. I don't have a super good way of finding this next constellation besides just telling you to look for its asterism. These 4 stars right here form an asterism that is called the Great Square of Pegasus. And it's called that not just because it is a pretty great square. Come on, you gotta look at those sides. But because it is in the constellation of Pegasus, the winged horse. Now, Pegasus is pretty interesting because it does what few constellations do. It shares a star with another constellation. This star right here is called Alpheratz. And Alpheratz is a shared mutual star between Pegasus, the flying horse, and Andromeda, the daughter of Cassiopeia and Cepheus. Now, Andromeda is a pretty alright constellation in and of herself, but the reason that we really like talking about Andromeda is because of an object that you can find right above what I affectionately call the kneecap of Andromeda. And that object is right here. It is not a star, but... No, that's not it. What are you trying to play at? There we go. Right here. Now, you have to be in a pretty dark area to see it. But it's gonna... If you are in a really dark area, you'll see it as kind of like a haze. It is not a star, but a huge collection of stars called the Andromeda Galaxy. And the Andromeda Galaxy is our nearest galactic major, one of the closest major galaxy to us. It is not the closest galaxy per se to us, but it is the closest one worth mentioning. That being said, it is still about 2.5 million light years away. Now, I used the word light year briefly before, and I very quickly said that 1 light year is about 6 trillion miles. Not only is the Andromeda Galaxy our nearest galactic neighbor, but it's getting closer. In about 4 billion years, roughly 4 billion years, the Andromeda Galaxy and our home galaxy, the Milky Way galaxy, are going to collide. In about 4 billion years, if humans got to the point where we could leave the Earth and go to different solar systems, because by the time 4 billion years rolls around, our sun would have made it impossible for life to exist on Earth anymore. We won't likely... I don't know when humans are going to go out, but with a lot of assurity, I can tell you that there is going to be no type of life on Earth guaranteed in just about 1 billion years. Because by that point, the sun will have begun to go into a different phase where it begins to swell up and it's going to make it so that Earth just cannot have life on it anymore. It's going to strip Earth's atmosphere away. It's going to boil our oceans. No life is going to exist on Earth in 1 billion years. Nothing. But if humans were able to leave Earth before then, and humans were still alive during this great galactic collision, likely, we'd probably be fine. There is so much space between stars in a galaxy that it won't be so much of a collision, then it will be a merger. These two great galaxies will slip in and out of each other, throwing stars this way and that way, ensuing in another billion-year-long cosmic dance until they finally calm down and come together to form one new galaxy, which unimaginative astronomers have already named Milkdromeda. If you don't like that name, if you think it's too silly, one, don't blame you. Astronomers are really bad at naming things. And two, if you have a better name for it, you have 4 billion years to convince whatever space agency we have at the time, or NASA, to come up with a better name. Now, if you took a telescope, like just a normal telescope, any of our telescopes, even larger, like basic visual observatory telescopes, if you point it at Andromeda, you're probably just going to see a slightly bigger smudge. For the most part, Andromeda is not very bright. When we see the smudge further away, Stellarium is not a good representation of this. But when you see the smudge, what you're seeing is not the entire Andromeda Galaxy. You are just seeing the incredibly bright core of billions of stars swirling around Andromeda's supermassive black hole. So it is that smudge is visible with the naked eye, and when you look at it, you do know that you are looking at at billions of stars, dozens, at least a dozen trillion miles away. And that's just, I don't know, that's a humbling feeling. That's a fun feeling. Because how often do you ever look and actually see a billion of anything? But you can get that by looking at that smudge of Andromeda, the collective light of billions of stars. Now, as we move on through the fall months, we have the most anticipated constellation coming up over the horizon. In November, probably even a little... No, yeah, in about November. In the early evening, again, we're sitting at about 9:30, we will see the famous constellation of Orion the Hunter peeking up over our horizon. And we all, people always ask during summer shows, like, can you show me where Orion is? And that's a completely reasonable question. Orion's a fantastic constellation, and everyone wants to know where Orion's at. Completely understandable. But you can't see Orion during the summertime because, well, we go back to season changes. As the Earth orbits the Sun appears to get in front of us and other constellations. So, right around here is the Orion Constellation, right? During December, the Sun is on the opposite side of the Earth from where we would see the Orion Constellation. But during the summer months, June, the Sun is in between us and where we would see the Orion Constellation. During the early summer months, Orion is high up in the sky at noon, but so is the Sun. And when the Sun is up, it scatters its light throughout our atmosphere, causing it to glow that romantic blue color we think of a clear summer day. And when that happens, you can't see any star in the nighttime sky. But as we can see with the Sun moving, it only blocks out a very few amount of stars at any given point of the year. We often, when I talk about things, I usually talk about them when I say summer, fall, winter, spring constellations. We refer to those constellations as what you see in the early evening after the sun sets. But in actuality, towards the middle of June, or towards the middle of summer, what's called a cross-quarter day, what day is that? I think it's Lammas. The cross-quarter day between June and September. I think that's a Christian holiday. Not really sure what Lammas is. I think I remember it being something about bread. But, during the cross-quarter day in between June and September, you're able to see Orion again, not in the evening, but in the morning. So, like, a couple months through summer, you can start seeing Orion again. You just have to wake up early, rather than going out early in the evening. And then it just comes out sooner and sooner throughout the months until we reach November, where it is in our early evening sky again around 9:30. So you'll be able to see Orion again with its famously bright stars, Betelgeuse and Rigel. And you can use his belt stars, because if we connect all three stars together, they point up to a bright red star named Aldebaran, which is the Eye of the Bull, which is another one of our zodiacal constellations. Cetus is not a zodiacal constellation. I accidentally clicked him. But Aries is. So Pisces, Aries, Taurus. If we use Rigel and Betelgeuse, he will point up to Gemini, the twins. So these are the constellations that are most notable throughout the fall months. Now again, you can see Orion this evening if you wanted to, but you would have to wait until about 2 in the morning when he'll rise up over the horizon. But with that said, I do want to take a moment to just plug our next show coming up, which is on Halloween, the 31st, When Stars Go Dark, a show where we take actually terrifying things about science and space and do what Halloween is for. Try to spook the people who watch the show with very real, very possible events that could occur. I'm really excited about this show. We have our last last year's When Stars Go Dark up, where we talked about Jack Parsons, a Greek woman who was dragged and viciously murdered. She was like, she was a really prolific scientific mind at that time, and how the universe is going to end. Hypatia. Talked about Hypatia last time. So these were all in last year's show, and we have some new, even more terrifying concepts events for this upcoming Halloween show. With that said, I will keep it up just in case that it is going well right now. I'm gonna stick around in case anyone has any extra questions about what we talked about, or other things about science or astronomy or physics that you've been dying to know and haven't been able to get a good answer to. We'll try our best. If we also don't know the answer, we know where to look, and we'll try to help you find that answer, and we'll post it later on. But with that said, if you're ready to go, I want to thank you guys for sticking through the show. I want to thank you for coming. I encourage you guys to come back, learn more, never stop asking questions, never be afraid to ask questions, because there's so much about space and science and the world around us that we don't know, and so much that we can all still learn together.